not bad?
Yeah, it's not too bad, but okay. Well, good morning. So, just some quick announcements, I guess. Quiz 8 is going to cover. It's going to be on next Monday, and it'll close on next Tuesday, covering lessons 21, 22. Quiz 9 is going to be this Friday, or not next Friday, next Friday, October 30th to Saturday the 31st, so Halloween, and covers lessons 23 and 24. So, yeah. Any questions on anything? Any homework questions you want to look at? Anything? Okay. Well, okay. So, as I mentioned a couple minutes ago, today's goal is essentially just going to be the following. So, evaluate the limit as x goes to infinity of f of x, and the limit as x goes to negative infinity of f of x. Okay, so basically the idea is that in this case, we still have limits, but the idea now is that now x becomes a really large positive, or respectively negative, number. Okay? So that's basically the idea behind what these limits are. So if you let x go to infinity, basically you're just letting x get larger and larger and larger as a positive number, and it's not stopping, basically. And similarly with this, it's just you're letting x be a really, really, really big negative number, essentially. Okay? So to get an idea of what's going on with these types of limits, let's go ahead and look at this first example. Since there's no really other theory behind this, it's just, here's our goal, now let's do examples. So basically the first thing we're going to do is we're going to use this table below to deduce the limit as x goes to infinity of 1 over x. So what we're going to do is say, all right, well, if we let x equal 10, and we let f of x equal 1 over x, then let's go ahead and fill this table in. So if x equals 10, then f of x would equal what? Yeah, 1 over 10, right? Or as a decimal, that would just be what?
0.1.
Yeah, 0.1, right? Okay. And then from there, we just sort of just keep going down to 1, right? So if x equals 100, then 1 over x is?
0.01.
Yep, 0.01. And then someone else, what would the next thing be?
0.001.
Yep, 0.001. And then from there, you kind of get the idea. If x equals 10,000, it would be 0.0001. Okay? So basically the pattern you notice is that as x gets larger, 1 over x, what happens to 1 over x? So as x gets larger and larger, 1 over x gets smaller and smaller. Good. So as a result of this, what should that tell you about the limit as x goes to infinity of 1 over x?
Or to 0.
Yeah, it just goes to 0, right? And that's it. That's example 1. Okay. So, any questions on that? Okay. All right, so now let's move on to example 2 then. So, similar idea, except now we're just going to go ahead and go straight to evaluating the limits. So, now let's consider the limit as x goes to negative infinity of 1 over x. So, what you notice is that in this case, all we're really doing is, instead of letting x be a really, really big positive number, the negative infinity means we're now letting x become a really, really big negative number. But even then, what do you notice? So even if x becomes larger and larger, regardless of sign, what happens to 1 over x?
So it's not.
Right. So in that case, that means similar reasoning as in example 1 says that the limit as x goes to negative infinity of 1 over x should equal what?
Zero.
Yeah, just big fat 0, right? Okay. So that's that one, and then the limit, now let's do the same thing for the limit as x goes to positive infinity of 3 over x squared. Now you may think, okay, well now it's x squared instead of just x, but even still, same idea, right? In this case, but the only difference now is that if x it goes to infinity, this x squared just means that this part here goes up, this x squared just goes to infinity faster. So if that's the case, then what should that tell you about the limit as x goes to infinity of 3 divided by x squared? Someone else? Just to get a bit of variety. So 3 over x squared still gets smaller and smaller. So, past, there we go. Okay, so as x goes to infinity, this still becomes 3 over x squared still gets smaller and smaller by similar reasoning as in example 1, right? So what should that tell you about the limit there?
If it keeps getting smaller, it also goes through.
Yeah, it just goes to 0, right? So that's example 2. So now let's go to example 3. So now what we're going to do is we're going to evaluate these two limits here. So what you notice is that the only real difference between them is that in this case, the first limit has an x over 12 on the second term, and the second one has x squared on it. That's the only difference between them. So here's what's going to happen with this. So let's take a look at the first one just to get an idea of what's happening with this. So one nice thing about limits in general is that, so we have 20 over x cubed minus x over 12. So one nice thing about limits is that you can in some cases you can just focus on the limits of each individual term if applicable. So what I mean by that is that you can just, if you want to find the limit as x goes to negative infinity of this whole thing right here, what you can do sometimes is focus on the individual terms. So we have 20 over x cubed minus the limits as x goes to negative infinity of x over 12. So what do we notice with this? So if we take a look at this first thing here, well, similar reasoning as in the first two examples should tell you that this becomes what? This first term. Go ahead.
0.
Yeah, just 0, right? Then minus the limit as x goes to negative infinity of x over 12. So if that's the case, that says, all right, well, if x goes to negative infinity, well, what's going to happen with x here?
It's just going to become negative infinity.
Negative infinity, right? So negative infinity, because one way you can see this is that if you take a look at the graph of just x, you notice that the graph of f of x, so f of x equals x. So if you notice that if you let x go to negative infinity, that means that this is also going to go down to negative infinity as well. So that's the idea behind that. So then as a result, well, that should tell you that if you get rid of these two negatives, ultimately you're just left with positive infinity for the first part. Alright? Now let's do a similar thing except with the second example. So if x goes to negative infinity of 20 over x cubed minus x squared over 12, we have limits as x goes to infinity, negative infinity. 20 over x cubed minus limits as x goes to negative infinity of x squared over 12. So as before, this goes to 0 because it's the exact same thing we had above. So this is still 0. But now what happens with this? So one thing to note here is that if we take a look at the graph of x squared, so if this is x squared here, then what do we notice? So if x becomes a really, really large negative number, so it just keeps going left on the x-axis forever and ever, then what happens with x squared? Yeah, it's going to shoot up to positive infinity because of the graph. So if x goes to negative infinity in the negative x direction, that means that x squared is just going to keep going up to positive infinity. So as a result, you're going to have minus because of minus here, infinity. So in this case, you're going to end up with negative infinity for your answer. Okay, so that's example 3 in a nutshell. So any questions on any of that? Okay. So now here's where things get a bit more interesting. So now with example 4, we still have a rational function, but now it's a bit more complex than it normally is. So now we have the limit as x goes to positive infinity of 1 plus 2x minus x squared divided by 2x cubed minus 3. So here's the thing. So what you'll notice is that in some sense, we could set up table. Oops, if I can spell table, not table. Set up table as in example 1. But here's the thing with that. If we can still do that, but the catch is that this is a rather complex function to be dealing with here. So if there's a shorter way to do this, then that might be better. So the thing is, but computations can get messy. So instead, we're going to apply this general rule that's a bit easier to work with here. So here's our general rule. General rule. So the limits as x goes to plus or minus infinity of a rational function is determined by leading terms with highest powers of numerator, and denominator. Okay. So to give an idea of what I mean by this is that, for instance, x squared goes to infinity faster than x, x cubed goes to infinity faster than x squared, and so on and so forth. So the reason why we consider the highest powers here is that we say, all right, well, so for instance, if we have, say, an x squared and x, well, x squared is going to go to infinity faster, so we focus more on the leading term, the one with the highest power, because ultimately the one with the highest power is what's going to be going to infinity faster / the fastest, depending on the number of terms on the numerator / denominator. So what I mean by this is that we say, all right, so the leading terms with have the highest powers on them. So if we take a look at the numerator, well, we say, all right, well, the highest power on the numerator is a square. So that means the leading term is going to be negative x squared. And then similarly, if we use that similar reasoning on the denominator, then the leading term there should be what? Yeah, 2x cubed, because that's the one with the highest power. So as a result, so the limits as x goes to infinity of 1 plus 2x minus x squared over 2x cubed minus 3, well, that's the same thing as the limits as x goes to infinity of negative x squared over 2x cubed. Because in this case, we're just focusing on the highest powers here. So then, as a result of this, if we simplify this down a bit, well, if we simplify this function down a bit, we have the limit as x goes to infinity of what?
Negative 1 over 2x.
Yep, negative 1 over 2x, right? So as a result of that, we say, all right, so now ultimately the limit becomes just simplifying or / evaluating this, right? So what does this become? Raise your hand if you have it. Let's just, yeah, just 0, right? Because as x gets bigger and bigger, this ultimately becomes smaller and smaller because of the x downstairs. So as a result, you just have 0 as your final answer. Okay? So, any questions on that part? Okay. So, now that I said all that I really wanted to say on the idea of a limit at infinity, let's go ahead and apply this to something. So, now let's go ahead and move on to finding the asymptotes of a rational function. So, here are the 3 we're going to consider. So a vertical asymptote is the zeros, 0/zeros, depending on the number, of denominator when f of x is simplified and they exist. Okay? So that's the idea of a vertical asymptote. So the idea of a vertical asymptote is that it's going to be of the form x equals some number. Okay? A horizontal asymptote, meanwhile, is going to be of the form y equals some number, and that is found by evaluating the limit as x goes to plus or minus infinity of f of x. So the nice thing with this is that if either are finite, as in, it's not equal to plus or minus infinity, that is the horizontal asymptotes. Okay? Now, a slant asymptote, meanwhile, is going to be a little bit different. So, the idea behind a slant asymptote is that it's supposed to resemble some sort of line in this case. Or at least in the case of what we're going to be looking at. So in this case, it's going to be of the form y equals mx plus b. Now, something to note here is that a slant asymptote in this context is only going to occur when the degree of numerator is precisely one greater than the degree of the denominator. So what I mean by this is that the degree is basically corresponding to the highest power here. So, highest power. Degree is highest power. Okay? And if you want to find this, then we have to use what's known as polynomial long division. Long division. Okay. So any questions on any of that before we move on to our next example? Okay. Give you guys a minute to write that down. So we got plenty of time. Okay. All right. So let's go ahead and apply this to example 5 here. So in this case, now we have to consider the asymptotes of the following rational functions. So the first example is f of x equals 1 plus 2x minus x squared divided by 2x squared minus 3. So taking a look at this, we say, all right, so now let's start by finding the vertical asymptotes. So we might need a 0. So the vertical asymptote says, all right, so if we take a look at this, we say, all right, first off, is f of x simplified? As in, are there any factors that are common to both the numerator and denominator? Just by taking a look at the function. There aren't any, right? So no common factors between numerator and denominator. So f of x is simplified. Simplified. So now that f of x is simplified, that just means now we have to focus on the zeros of the denominator. So, taking a look at said denominator, we have 2x squared minus 3. We set that equal to 0. Then what should that tell you about the vertical asymptotes or vertical asymptotes here? We solve for 0 here, or solve for x here. So raise your hand if you can see what the asymptotes would be here. Yep. Because what you notice is that if we solve for x squared, then we have, well, you should get 3 halves out of this. Then, as a result, if you square both sides, then we have x equals plus or minus the square root of 3 halves. So those would be your 2 vertical asymptotes in this case. Okay. So those are the vertical asymptotes. Now let's take a look at the horizontal asymptotes. as before, let's go ahead and say, all right, we have to evaluate the limit as x goes to plus or minus infinity. So let's start by considering the limit as x goes to infinity of our function. So we have 1 plus 2x minus x squared divided by 2x squared minus 3. Okay. So if we take a page from what we did back in example 4, then what should we do with how to simplify this down a bit? Go ahead.
Plot the highest power on the top and the bottom.
Okay, so what would those be here?
So it'd be negative x squared over 2x squared.
Gotcha, right. So in that case, the limit as x goes to infinity of this function here is the same thing as the same limit of negative x squared over 2x squared, right? But wait a minute. There's both an x squared on top and bottom, so that might make things a lot easier on us. So the limit as x goes to infinity of this just becomes negative 1/2, right? So that should tell you that the limit as x goes to infinity of f of x is just what?
Negative 1/2.
Just negative 1/2, right? So as a result of this, if we use similar logic, the limit as x goes to negative infinity of f of x, so 1 plus 2x minus x squared over 2x squared minus 3. So if we use similar reasoning as back up here, then what should that tell you about the limit as x goes to negative infinity? Yeah, just negative 1/2 again, right? Because as before, we just have to take the highest and lowest, take the highest power on top and bottom. So you should still get this out of it. So we have the limit as x goes to negative infinity of negative x squared over 2x squared. And then the nice thing is the same simplification results, so you should have negative 1/2 inside the limit. So negative 1/2 will be the limit again. So, as a result, you should have that y is equal to negative 1/2. Okay? Okay, so that's going to give you the horizontal asymptote. So, now let's take a look at the slant asymptote. So, this one's going to be pretty nice. So, take a look at the slant asymptote. So remember, the only way a slant asymptote exists is that if the degree of the numerator is exactly 1 greater than the degree of the denominator. But is that true here? It's not, is it? So none by definition. Okay. So one thing to note here is that, so generally, f of x will not have both a horizontal asymptote and a slant asymptote. Okay. So that's part A. So any questions on any of that? Okay, so now let's take a look at part B here. So if we take a look at this, well, so first off, we should probably check, okay, first off, is f of x simplified as much as possible here? So taking a look at the top and bottom, are there any common factors between them? No, there aren't, are there? So that should pretty quickly tell you that yes, f of x is simplified in this case. So now let's start by finding the vertical asymptote here. So in this case, that should be pretty nice and quick. So if we just set this denominator here, x minus 3 equal to 0, well, that should pretty quickly tell you that x should equal 1. 3, good. So that's the vertical asymptote, so nothing crazy there. But now let's make things a bit more interesting. So if we focus on the horizontal asymptote now, and we have the limit as x goes to infinity of 1 plus x minus x squared over x minus 3, well, if we sort of keep doing what we've been doing and focusing on the highest powers on top and bottom, what's going to happen here? Go ahead.
It's going to become negative x squared over x, which will simplify to negative x.
Right, so there's the catch there, though. So we have negative x squared over x, so we have negative x squared over x, which, as you said, is just going to simplify to negative x. So as a result, that should give you what as your limit value? Yeah.
0?
It's not going to be 0. So in this case, x is just going to get larger and larger here, right?
So
Yeah. Well, because it negative infinity because of the negative. So the only way we have 0 at all is if the x is downstairs, essentially. Okay. And then similarly, if we do the same thing with the limit as x goes to negative infinity of 1 plus x minus x squared over x minus 3, then if we apply the same train of logic that we just did here, then what would the limit as x goes to negative infinity be? Go ahead.
Infinity.
Infinity, right? Because the thing is that you're still going to have, x squared, negative x squared over x, which is just the limit as x goes to negative infinity of negative x. So then ultimately, you're just going to be left with negative times negative infinity, so positive infinity. Okay? So what that will tell you is that, well, no vertical asymptotes. So that's that part. But now is where things get a bit more interesting. Because now our slant asymptote is going to be where things start happening. So if you take a look at our conditions here, we say, all right, well, a slant asymptote exists when the degree of the numerator, in this case 2, is precisely 1 greater than the degree of the denominator. So does that happen here? It does. So degree of numerator is precisely 1 greater than the degree of the denominator. So that implies our slant asymptote exists. Okay? So in this case, our degree here is 2, and the degree of the denominator is 1. So yeah, that should pretty quickly tell you that a slant asymptote exists here. So now, the problem says, at this point, we have to find our slant asymptote by polynomial long division. So here's what that means. So what's going to happen here is that we are basically going to have to use that box for division that you guys have been seeing in K through 12 and K through 12 math. So what I mean by this is that we're essentially going to have this box here, and the denominator x minus 3 is going to be to the left of said box, while the numerator is going to be inside here. And what I'm going to do is I'm going to rewrite our numerator here, so that way the leading term is in front, and then followed by any terms that have a smaller degree. So negative x squared plus x, because that's the next leading term, next highest leading term, and then plus 1. Okay? So taking a look at this, we say, all right, so polynomial division, long division steps. Okay? So what's going to happen here? So the first step, so we have to divide leading term outside with leading term inside box. Okay. So let's go ahead and do that. So in this case, we have to divide the leading term outside, so in this case x, with the leading term inside, so negative x squared. So if we do that, we say, all right, well, so in this case we say, all right, so if we do that, what should we end up with? So we have negative x squared over x, so that should simplify to what? Yeah, negative x, right? So once we have that, step 2, so in this case what we do is that we take that ratio and put it right here. That simplified ratio and put it right here. Okay? So now that we have that, step 2, multiply results from 1, so in this case negative x, with polynomial outside. Okay? So in this case, we say, all right, we take negative x and multiply with x minus 3, right? So if we multiply those two, what should we get as our answer, as our simplified answer? So negative x times x minus 3.
Negative squared plus 3x.
Right. So in this case, we're now going to put our result directly below this. So we have negative x squared plus 3x. And the reason we're doing that and we're putting it precisely there is because step 3 is we have to subtract results from step 2 from polynomial inside and bring down next term. Okay? So what we're going to do is say, okay, we take the result from step 2, bring it here, and then we have to subtract it from the inside polynomial here. So if we do that, then what should we get as our simplified results?
Negative 2x
Yep, so negative 2x plus 1, right? Because the thing is that what should be happening is that these two leading terms should always cancel each other out, is what should be happening with polynomial long division. If that's not happening, you need to check your work in steps 1 and 2. Okay? So now from this, we say, all right, well, that's all we can really do with that, but step 4 now says, okay, now we just have to repeat these 3 steps here until a certain condition happens. So repeat 1 through 3 until you remain with a polynomial with degree less than that of outside polynomial. Okay. So basically what that says is that, all right, well, if we check our polynomial down here, we have to make sure that this has degree strictly less than the polynomial outside here. So if that's the case, well, if the degree here is actually less than the degree of the outside polynomial, we're done. But are we though? We're not. So we got to do this another time. So now let's move back to step 1, except now our inside polynomial becomes this, negative 2x plus 1 here. So in this case, we say, all right, now we have our leading term becomes negative 2x instead of negative x squared. So if we repeat step 1, then what should our result be? Right. So now we put negative 2 over here. So now we multiply result from 1, so in this case negative 2, with the polynomial outside. So if we multiply negative 2 with x minus 3, then what's our resulting polynomial? Negative 2x plus 6. Okay? So that's step 2. Then step 3 says, all right, subtract this polynomial here from this guy over here. Okay? So if we do that, then what would our resulting polynomial be?
Negative 5.
Negative 5. Good. Okay? So now step 4 says, okay, do we now have a polynomial that has degree less than that of the outside polynomial? We do, right? So that means stop here. So now that we have that, that says, okay, our polynomial then our slant asymptotes then becomes y equals negative x minus 2. Just the result of this guy up here, above the box. Okay? So that's part B essentially. That's how we find slant asymptotes with polynomial long division. Okay? So any questions on any of that? Okay, well, that's all I have for today. So, a question?
So would the answer just be negative x minus 2?
Yeah, this would be your slant asymptotes.
Do you not do anything with the remainder? Or
Yeah, we don't have to worry about the remainder because all we care about in this case is just the slant asymptote. So we don't care about the remainder. Okay?
Can I see the first page real quick?
Sure. One second. Let me see if I can find it. There we are. Does anyone else still need this? Okay.
What
Okay.
lessons or today's quiz on?
There's no quiz today.
What was the quiz?
The next quiz is. Wait a second. Wait a minute. Wait a second. Hold on. I should probably check this. 1 second. Piazza. Oh, okay. For some reason, I thought the quiz was on Monday. I'm like, okay, that's okay. My bad.
Okay.
So yeah, let me fix that. So quiz 7. So that's today. It's 10:21 to Thursday 10:22. Lessons 19 and 20. Okay. No problem. I thought for some reason we already did the quiz. Wait, what are you talking about? Oh, the quiz we're doing today. Okay. Right, that one. Okay. All right. Any other questions on anything? Okay. Well, that's, like I said, that's all I have for today, so enjoy your 5 extra minutes of freedom, and I will see you guys on Friday. Unless you guys have any questions on Zoom office hours, of course. But